Morning everyone. I am Badiaa Ahmed, a researcher in telecommunication and electronic engineering from the Medical Technology Group at the Institute of Astrophysics of the Canary Islands, Spain. As a co-author, I will be presenting this work when the first author is the PhD student Rabab Sedrati under the supervision of Professor Otman Aghzout from the National School of Applied Sciences of Tétouan at Abdelmalek Saadi University. It is an honor to have the opportunity to present our research entitled Enhancing Radiation Stability and Image Quality in Periodic Planar Structures, a characteristic mode analysis approach for cancer imaging. Before I begin my presentation, I would like to thank all the responsible staff for organizing this event and providing us with this opportunity. I also extend my gratitude to the reviewers to evaluate this work, and of course to all the authors from different institutions for their valuable contributions. Before I begin, I would like to provide an outline of the structure of our presentation. We have divided our talk into three main sections. Firstly, a brief introduction where I will provide background information on our research topic and explain its significance. Secondly, the section on model analysis of square planar structures, where I will describe the methodology used in our research and present the key results. Lastly, we will conclude with conclusion and future works, where I will summarize the main points covered in my presentation. So let's start by the introduction. As you are aware, antennas play a crucial role in a variety of fields from telecommunication to aerospace and military applications. In telecommunications, antennas facilitate the transmission and reception of radio waves, enabling long-distance communication between peoples. In military applications, antennas are integral component of communication and radar system for object detection and tracking. In the aerospace industry, antennas are essential for navigation, communication, and remote sensing. Our focus in this study lays within the realm of medical technology, particularly medical imaging engineering. So antennas are important in various medical imaging techniques such as magnetic resonance imaging, computed tomography, and ultrasound. They are utilized to both generate and receive electromagnetic waves, providing detailed images of the body's internal structures. Additionally, antennas are employed to transmit and receive high-frequency sound waves, enabling the generation of images of organs and tissues. Over the years, researchers have developed various methods for designing and analyzing antennas, including analytical, numerical, and experimental approaches. In our study, we employed the characteristic mode analysis method that is based on the principle that any arbitrary antenna structure can be expressed as a linear combination of its characteristic modes. These modes are those that predominantly influence the behavior of the antenna, such as its radiation pattern or impedance. By analyzing these characteristic modes, we can gain insights into the fundamental behavior of the antenna and identify design principles to optimize its performance. So, characteristic mode analysis offers several advantages over classical electromagnetic modes for analyzing complex structures. Some of these advantages include mode identification, high efficiency, robustness analysis, design optimization, better accuracy, and wide range of applications. As illustrated in the diagnostic workflow scenario presented in Figure 1, our optimized periodic structure with slots has been demonstrated to enhance the resolution of medical imaging. So medical professionals can now utilize our technology to acquire high-resolution images with reduced noise. Now we move to the second main section, where I will present all the results obtained from this work, and I will start with the first study. Our research methodology focused on analyzing the characteristic modes in free space environment and evaluating the characteristic angle, quality factor, and radiation pattern for each individual radiating mode within the frequency range of 20 to 44 GHz. In the first study, we analyzed a square plate and its divided shape. So figure 2 illustrates the geometry of our structures, while the accompanying table provides the parameters associated with these geometries. For the result obtained, the first analyzed structure is the square metallic plate, and as you can see from figure 3, this plate supports 5 radiating modes that resonate at different frequencies, with G1 and G2 are symmetric modes that resonate at 22.41 GHz. The results also show that G5, which resonates at 28.41 GHz, has the highest quality factor of 19.13, indicating that this mode is highly damped and has a large amount of energy stored in the resonant mode. Furthermore, G5 is the only mode with a bandwidth of 5.56, which suggests that it may be suitable for wideband applications due to its high quality factor and wide bandwidth. And based on the information provided by the characteristic angle curves and the table 2, the radiating bandwidth of the modes G1, G2, G3, and G4 of the square plates would be considered infinite. The radiation pattern in figure 4 of each radiating mode associated with the square plate is plotted at the resonance frequency of these modes and normalized to its maximum value. The second part of this study is about a square metallic plate that has been divided into 4 smaller patches of equal size. Figure 5 illustrates the frequency variation as a function of the characteristic angle for the first electric resonance modes of this structure. Our analysis has revealed the presence of 5 distinct resonance modes. These results provide crucial insights into the resonance behavior of the periodic structure and could play an important role in the development of optimized designs for medical imaging applications. By focusing on the characteristic angle, quality factor, and radiation pattern for each individual radiating mode, the results demonstrate that the divided plates exhibit higher quality factor and lower energy losses at frequencies corresponding to modes G3 and G4 around 35 GHz, indicating better performance compared to the undivided square plate. These findings suggest that the divided plate is better suited for applications that require high quality factor modes. Our study proves that the divided structure presented a significantly more stable radiation pattern compared to the original square metallic plate. In particular, we observed that the unwanted radiation pattern associated with mode G1 in the square plates become much more suitable at the frequency of 26.46 GHz when implemented in the divided plate. The introduction of slots on planar antennas has proven to be an effective solution for enhancing the performance of microwave and millimeter wave applications. This modification provides an increase in directivity, radiation efficiency, and impedance matching compared to the conventional planar antennas. Additionally, the slot plays a crucial role in medical imaging engineering by improving image resolution and reducing side lobes. By introducing a slot as illustrated in Figure 7, the planar antennas can operate at higher frequencies, thus providing an important improvement in the performance of wireless communication systems and medical imaging devices. And this is what we will see in the next slide. The addition of a slot to the original square metallic plate has led to new resonance characteristics for the structures. This new structure now plays 4 model labels G1, G2, G3, and G4 at frequencies of 23.49 GHz, 38.63 GHz, and 27.7 GHz respectively. So, modes G2 and G3 are seen to have the same resonance frequency and quality factor of 2.30 as mentioned in the table 5. The radiation pattern of the first electric modes of slotted square plates is depicted in figure 9, indicating that the slotted structure offers greater stability for mode G4 at 27.7 GHz compared to the mode G5 at 28.41 GHz in the original metallic square. Now, we arrive at the last analyzed structure in this study. The result of the analysis after introducing the slots to the divided metallic plate indicates that there are now 8 radiation modes compressing 2 pairs of symmetric modes G1, G2, and G6, G7, with all radiating modes exhibiting finite bandwidth compared to the previous results as depicted in figure 10. This increase in the number of radiating modes and their finite bandwidth could lead to enhanced radiation pattern stability and improved performance of the structure for medical applications, of course. This is because a periodic structure is generated when the structure is divided, leading to a more controlled and predictable behavior of the electromagnetic fields within the structure, resulting in improved quality factor and a better radiation pattern, as depicted in figure 11. Therefore, the slotted periodic structure has the ability to radiate more efficiently, which can offer enhanced performance in medical applications. So, as I come to the end of my presentation, I would like to take a moment to summarize the main points that we have covered today in this presentation. So, firstly, the studying periodic structures with slots can greatly enhance medical imaging applications, particularly in the early detection and the diagnostics of cancerous cells. Secondly, the introduction of slots improves radiation pattern stability and performance, leading to higher resolution images with increased radiation modes and improved bandwidth. And thirdly, it is important to consider the electromagnetic properties of structures when designing medical imaging structures. Moving forward, there are several avenues for future research in this area that could build upon the findings of this study. For example, experimental validation, that is very important, device miniaturization, and also the clinical trial it's necessary, and integration of the periodic structures and slots with other imaging modalities. So that conclude our presentation. I would like to express my gratitude to all of you for your attention, and I hope that this presentation has provided you with a clearer understanding of the potential impact of this technology on the healthcare and highlighted the importance of continued research in this field. I would like to open the floor for any question or propositions you may have, and thank you once again.